Alright guys, welcome back. Today we're going to be talking about Boyles' law, Charles' law, and Gay-Lussac's law. I'm assuming that you know them, so we're not going to go over them and belabor that. We're just going to start using them. Alright, you're wearing some scuba gear, you're swimming underwater, and you're breathing air, and you realize your air supply is low, so you hold your breath and then you come up. Okay? So what happens? Well, it's kind of like your lungs are kind of like a bag. Think of it that way. Right? And so here are your lungs, right? And they have a certain amount of air in them. Well, of course, think about what happens to a bag of potato chips as you go up to the top of a mountain. You know what happens there. Well, the same thing is happening here. The amount of air in your lungs isn't changing because you're holding your breath, right? But what's happening is the pressure that's pushing on the outside is changing. So if you're 66 feet underwater, you're at 3 atmospheres of pressure. Okay, but if you come up to the surface, you're at 1 atmosphere of pressure. So there's a lot less pressure pushing on the outside of these lungs. Just like there's a lot less pressure pushing on the potato chip bag in Hawaii as you get to the top of a mountain. And as a result, the bag exploded. So what would happen to your lungs? Guess what, folks? Same thing. Okay, so let's go and see exactly what's happening. We're talking about, we're ignoring temperature. So what we have is we have Boyles' law, which is pressure volume is equal to the pressure volume of the final system. All right. So your initial pressure is 3 atmospheres, and your initial volume is, let's say, 10.0 liters. All right, that's atmospheres. And your final pressure is 1 atmosphere. And your final volume is what you're questioning. It's going to be in liters. So if we take 3, we multiply by 10, divide by 1. Right? Guys, this is simply algebra, right? And I'm not going to sit here and waste any time doing algebra because I'm assuming you can do algebra. This gives you a volume of 30 liters. So your lungs have tripled from 10 liters in size to 30 liters in size. They've done it very quickly. Guess what? Your lungs can't do that. So your lungs explode. Okay? Not pretty. All right. What do we notice about problem 2? You notice that temperature remains constant. Since temperature remains constant, we have pressure 1, volume 1 equals pressure 2, volume 2. Again, we have Boyles' law. We're starting with 4 liters, which is your pressure, and 0.90 atmospheres. Sorry, the first one's volume. This one's pressure. And we're allowing it to expand until the pressure drops. So this is your second pressure. So what we have is pressure 1 is 0.90 atmospheres. And volume 1 is 4.0 liters. And that's equal to 0.20 atmospheres times some number of liters. All right? Now, folks, what you should notice here is all of our units, we have atmospheres and we've got liters on both sides. Our units balance. So when we divide by atmospheres, so we have 0.90 atmospheres, and we multiply by 4.0 liters, and we divide by 0.20 atmospheres. Our atmospheres are going to cancel. We're left with liters, which is what we want, and our answer here is going to be 18 liters. All right. Now, folks, if you've got questions about the math, of how to do the math and how to cross-multiply and that kind of stuff and the algebra, please come see us. We'll teach you the math, but you have to know the math, right? It's not magic. You have to know how to do the math. All right. We will notice here our temperature does not change. So, again, we're going to be able to use Boyles' law, which is pressure 1, volume 1 equals pressure 2, volume 2. And we're starting with an initial volume of 6.0 liters, and our initial pressure is 1.0 atmospheres, and our final volume is 1.90 millimeters of mercury. Okay, now, what I'm going to do is I notice that I've got atmospheres and I got millimeters of mercury as my units. That's a problem. I have to be consistent. Folks, it does not matter which way you go. It doesn't matter whether you go to atmospheres or whether you go to millimeters of mercury, right? So I'm going to happen to choose to do the 190 millimeters of mercury, and I'm going to convert that to atmospheres. Millimeters of mercury to atmospheres. And that means I divide by 760. All right? And this is going to give me 0.250 atmospheres. All right? So that's pretty easy. Now, because I've got atmospheres, I can work the problem. Again, you could have done the entire thing in millimeters of mercury. Would have worked exactly the same way. Right? Would have come up with exactly the same answer. So my initial pressure is 1.0 atmospheres. My initial pressure is 1.0 atmospheres. My initial volume is 6.0 liters. And that's equal to my final pressure, which is 0.250 atmospheres. Notice I've got my atmospheres on both sides because I have to cancel them, right? Times my unknown number of liters. So when I take the 1.0 atmospheres, multiply by the 6.0 liters, divide by the 0.250 atmospheres, that's going to give me 24 liters of a gas. All right, let's try number 4. All right, let's see. We have, what is the temperature of the air of the tire? So the temperature is clearly changing here, and our pressure is changing. And we have a car tire, so we're assuming that the volume is not changing. So what I can use here is P1 over T1 equals P2 over T2. Right? So let's go and see what we have. We have atmospheres, and we have atmospheres, so that's initial pressure, final pressure, that's cool. Temperature, T1, oops, it's in Celsius. I have to convert to Kelvin. 27 degrees Celsius plus 273 gives me 300 Kelvin. Okay, so that's easy. All right, do I need to do any other conversions? I don't think so. So let's go ahead and do our problem. So our pressure is 2.0 atmospheres ATM, divided by our initial temperature, which is 300 Kelvin. Remember, your temperature must always be in Kelvin. Your second pressure is 2.2 atmospheres. And your final pressure, your unknown, is in Kelvin. All right? So let's go ahead and do this problem. How do you do it? Well, the easiest way to do it is cross-multiply. So you have 300 Kelvin times 2.2 atmospheres. You divide by what's left, which is 2.0 atmospheres. Atmospheres cancel. I'm left with Kelvin. So when I do the math, I come up with 330 Kelvin. So, guys, that's a perfectly legitimate answer, 330 Kelvin, because I didn't say that the temperature had to be in Celsius. So that's an okay answer, all right? But I don't think in Kelvin, I think in Celsius. So I'm going to take 330 Kelvin. I'm going to subtract 273 from it because that makes so much more sense to me. And that is 57 degrees Celsius. All right? So that's what I would do. All right? So for me, I would rather have the answer as 57 Celsius. All right. Let's try number 5. I have 5.0 liters of air at negative 50 Celsius. It's warmed to 100 Celsius, so my temperature is changing. My volume's changing. My pressure's constant, so I don't have to worry about my pressure. So it's going to be volume over temperature equals volume over temperature. All right, so my volume is 5.0 liters divided by my temperature. Oops, my temperature is in Celsius. So negative 50 Celsius plus 273 is going to give me 223 Kelvin. Oh, and my final temperature, I might as well do that right now. There's 100 degrees Celsius. Add 273, and that gives me 373 Kelvin. All right, so I put 273 Kelvin down here on the bottom. Isn't it wonderful to have trash pickup? That's what you're hearing in the background. Is an unknown number of liters over 373. I didn't do that right. That's 223 Kelvin. 373 Kelvin. Right, so I do cross multiplication. 5.0 liters times 373 Kelvin divided by 223 Kelvin, because that's what's left, and that's going to give me 8.36, or if I round, 8.4 liters. Right, so that's my final answer for number 5. All right, number 6, 10 atmospheres of pressure, 20 degrees Celsius. All right, well, let's change these. 20 degrees Celsius, I have to add 273, so that's 293 Kelvin. And here I have to add 273 to 50, so that's 320. 273 is 323 Kelvin. Okay, what's the pressure? So my volume is remaining steady, so I don't have to worry about volume. So it's pressure 1 over temperature 1 equals pressure 2 over temperature 2. This temperature is going to be 293 Kelvin. This one's going to be 323 Kelvin. And my initial temperature, my initial pressure is 10 atmospheres. So the question is, what's this one? All right, so I take the 10 atmospheres, I multiply by 323 Kelvin, I divide by 293 Kelvin because that's what's left. My Kelvins cancel, I'm left with atmospheres. Okay, and I come up with, let's see, I had 2 sig figs in my answer, so it's going to be 11 atmospheres of pressure. That's my answer. Okay, number 7. I have a bike tire, pressure's changing, temperature's changing, volume is remaining constant. All right. So do I need to put that volume in? It gives me a number for it. No, you don't. Doesn't matter. So long as the volume remains constant, we can ignore it. So we have 40 psi. That's cool. We have Celsius temperatures. All right, let's see. That's going to be 273, obviously. And 35 plus 273, 273. Is equal to 308 Kelvin. So let's go ahead and do that. So I have pressure 1, temperature 1 equals pressure 2, temperature 2. So my initial pressure is 40 psi. My initial temperature is 273 Kelvin. And my final temperature is 308 Kelvin. And this is my unknown, and it's going to be in psi. Because my units have to balance. So I have 40 psi times 308 Kelvin, and I divide by 273 Kelvin, and that's going to give me 45. Again, rounded to 2 sig figs, because there's 2 sig figs right there. 45 psi. All right, that's number 7. I need a few more to go. Right. A hot air balloon has a volume of 10,000 liters. Notice there is a decimal point there. There are 5 sig figs there. Right. So let's see. My temperature is going from 25, which is 273 plus 25, gives me 298 Kelvin. And 65 plus 273, 273, gives me 338 Kelvin. And so let's actually do the math here. I've got volume over temperature because my pressure is remaining constant. Goes to volume 2 over temperature 2. Right? My initial volume is 10,000 liters. My initial temperature is 298 Kelvin. And my final liters are unknown, and my final temperature is 338 Kelvin. So I get 10,000 liters times 338 Kelvin divided by 298 Kelvin, and that's going to give me some big number. 1, let's see, how many sig figs can I have? Looks like about 3 here, so 11300 liters. All right, so that's number 8. How about number 9? Frankly, I'm not sure you'd be able to hold the bicycle pump. this long, but we can give it a shot. All right, let's see what's not changing. Well, our temperature, let's see. What is changing? Holds on to before the pressure is 20 psi. It's going to 80 psi, so my pressure is definitely changing. What fraction reduces the volume of the pump? All right. Well, what fraction? So I'm looking at volume. So let's assume the temperature remains the same. So if I have volume, I'm going from 20 psi. Now let's put our equation first. Right? We're saying temperature is remaining the same, so it's P1 V1 equals P2 V2. Right? So our initial pressure is 20. Our final pressure is 80. But what's our volume? Well, who knows? But you have a hint. And your hint says you're using 1 liter of air. So let's make that 1 liter and see what happens. Because then we'll figure out our volume. So we have 20 times 1 divided by 80 is going to give me 0.25. That's in liters. So that tells me that this thing went from 1 liter down to 0.25. Now that ratio is always going to be the same. So it went down to 1/4 or 25% of its original volume. All right, is what it now is. So we lost, so it went down by 3/4, or 75% is what it went down by. So it went to 25%, but it went down by 75%. So based on the way the question is phrased, by what fraction did he reduce the volume in the pump? You'd say 3/4 or 75% is what you reduced it by. All right, final question, I believe. We're looking for temperature, and we can see that the pressure is changing and the temperature is changing, so we're saying our volume is remaining constant. And you'll notice we have PSIs in both cases, so that's really nice. So we have 25 PSI, so we have temperature, so T1 and P1 is equal to P2 over T2. So our initial pressure is 25 PSI. Our final pressure is 30 PSI. Our initial temperature is -10. All right. -10 is going to be 273 minus 10 is 263. 263 Kelvin, and we're asking for what this number is. So we have 30 times 263 divided by 25. That number is going to give us 315.6 or 316. 315.6. Now that's in Kelvin. So I'm going to subtract 273. Again, I don't like Kelvin temperatures. They don't do much for me. All right, so I get 42.6. And that's degrees Celsius. And because I only have 2 sig figs in my problem everywhere, I'm going to take that to 43 degrees Celsius as my final answer. All right, folks, that's it. If you have questions, please see us in class. We'll be more than happy to help you. And have a great day. Bye-bye.